Good evening, everybody. Could you please stand for the academic procession as they will enter the hall? Please be seated.
Good afternoon, ladies and gentlemen. And the reason she said please be seated because I always forget, and then people stand for a long time. So thank you for making sure that they actually got their seats this time. Good afternoon. My name is Wikus van die Kerk. I'm currently the Dean of the Faculty of Engineering. And it's my pleasure to welcome everybody here for this inaugural lecture of Professor Herman Engelbrecht. I want to start and specifically welcome Professor Deresh Ramjugarnath, our DVC Learning and Teaching. Thank you very much for being here, Deresh. We also have our Vice Dean, Teaching and Quality Assurance here, and she did an excellent job because our XI accreditation went south, so Professor Celeste Viljoen. Then, apparently, we also have a future chair of the Department of Electrical and Electronic Engineering, Professor Jaapie Engelbrecht here. who, if you don't know, he's also the brother of Professor Engelbrecht. And then, of course, very importantly, we have Marianne, the wife of Professor Engelbrecht, and the children, Herman, Annemarie, and Adrian here. And they're sitting right at the back there. So normally it's the naughty students that sit at the back, right? So I'm just warning you, you have to live up to that expectation. Then we also have Professor Jaapie Engelbrecht, the father of Professor Engelbrecht here as well, and his wife. So, over there. Welcome here. We have Imker and Elsie Hoogenout, who are the parents-in-law of Professor Engelbrecht, and they are from Vereniging Learned. And then online, we also have the twin brother of Professor Engelbrecht, and he is Professor Skalk Engelbrecht. So if you see somebody today, you can say Professor Engelbrecht, and you'll probably get it right. So Skalk, baie dankie dat jy aanlyn is, en hierdie geleentheid ook aanlyn gaan bywoon. Then I see quite a number of other colleagues of the Department of Electrical and Electronic Engineering. There are a number of friends, collaborators, students, and all the other attending, both in person here with us and then also online. So everybody, I trust that you feel welcome now. So the procedures here is I'm going to do an introduction, then Professor Engelbrecht is going to deliver his address. Professor Ramjugarnath is going to respond to that, and then the other Professor Engelbrecht will do the vote of thanks. So to introduce Professor Herman Engelbrecht, he is a Stellenbosch University alumnus through and through. He enrolled for his undergraduate studies in electrical and electronic engineering in 1997, and he obtained his PhD in electronic engineering 10 years later. He co-founded the MIH Media Lab, and I see his fellow conspirator at that time is also around here, Gert-Jan. Baie dankie dat jy hier so is. So they founded the MIH Media Lab, which was then funded by NASPERS from 2008 to 2016, which graduated more than 61 postgraduate students. In 2013, he also co-founded Custos Media Technology and SU spin-off company with his partner in crime sitting over there. Sorry, I've lost my space here. He was responsible for the introduction in the data engineering curriculum of the Faculty of Engineering in 2019. And this year, we will graduate our first data engineers from the first intake in 2019. Unfortunately, there's only 11 left, but but there's still some others in the pipeline that we will help through this time. The class was only 30, so but it became a very popular program, so that was good work. And then he also served as the chair, and he's still serving as the chair of the Department of Electrical and Electronic Engineering. His research interests include distributed systems, specifically infrastructure to support massive multi-user virtual worlds, and machine learning, particularly deep reinforcement learning. And the aim of his research is to scale virtual worlds to enable more than 100,000 users to interact in a single contiguous virtual world. I've got no idea what that means, but I promise you in an hour's time we will know everything about this because Herman's going to explain that to us. He's also a registered professional engineer, a senior member of the Institute of Electrical and Electronic Engineering, or the IEEE as they are well known, and a member of the Association for Computing Machinery. And he's been rated by the National Research Foundation as a C2 scientist, which means that he is well known in his scientific community and in his field of expertise. So Herman, as you've heard, we are here, and you have to explain all these difficult words to us, and we are waiting in anticipation.
Thank you, Vikas. Thank you, Professor Ramjuganov. Yapi, thank you for graciously accepting my little joke. So thank you, everyone, esteemed guests, ladies and gentlemen. So, I've been fascinated by computer and video games since my father brought home a Sinclair ZX Spectrum 8-bit home computer with 48K of RAM. Yes, it was amazing. And I wanted to know, okay, but how do you use electronic circuits, which is basically transistors, resistors, capacitors, inductors, and build video games? Those two didn't really go together with me. So to figure that out, I decided to study electrical and electronic engineering, maybe with a focus on the electronic part. And then eventually that also led to my interest in virtual worlds and the metaverse. So I will, if I switch this on, I will start by introducing the metaverse. And part of that, I'll explain what's meant with virtual worlds, and I will also explain what's meant with virtual reality. And then, as part of that, I will also talk a bit about what the architectures used for virtual worlds. So I'm not going to be focusing on the computer graphics or the head-mounted displays. The idea is to focus on the servers and the server architectures needed for virtual worlds. Now, an important part of these worlds is where do you actually store them? Where are they stored? And if any changes are made to, like if it was Minecraft, to the blocks in the virtual world, how do you actually send all those changes to everyone participating in these virtual worlds? As I said, we want to go to 100,000 or even millions of users, so you have to send these changes to everyone so that everyone has a consistent view of the virtual world. And since we're talking about scaling to thousands or millions of users, I will then talk a bit about what are the architectures used to scale to thousands or hopefully millions of users. And then that's the how do we do things part of the lecture. And then I will talk a bit about some of the research projects that I've been privileged to be involved in over the past 10, 12 years. So the first project is something called the Third Life Project, which was a virtual reality type project that we did in 2015. Then we'll go slightly back to 2013. I will talk about the Kukapan project. And then the third project I will talk about is an extension of the Kukapan project called VAST, which is about spatial publish subscribe. I will then hopefully bring everything together and end with talking about some of the remaining challenges in building the metaverse, and also talk a bit about some major developments which happened in the past month or so. Okay, so, yes, this works. Yay. So what is the metaverse? What is this thing we call the metaverse? So the word or the term metaverse was actually first used by author Neil Stephenson in his 1992 novel Snow Crash. Okay, now, if you're looking for some weird 90s science fiction, this is quite an interesting book. It's got a freelance hacker / pizza delivery driver that works for the mafia, and that's only the first chapter. Right? So I can definitely recommend it, and I think it is important because I think it did have a major impact on people's way of thinking about the metaverse. But one thing which we do see is that the metaverse is a fusion of these two things. One is called virtual reality, and the other thing is called virtual worlds. So to explain the metaverse, I'm going to talk a bit about what is virtual reality, and then, well, first talk about virtual worlds, and then I will talk about what is virtual reality. So I did manage to actually, I was supposed to give this lecture in June, and I was graciously allowed to postpone it until now. You only get one get out of jail card for free, so that's why we're doing it now. But getting back to virtual reality, we're going to go back into history and look at what was the first virtual world. And the first virtual world that was developed in 1973/74. That's 50 years ago. It was called Maze War. There's a picture of it here on the right-hand side, left-hand side for you. And it was the first networked 3D multi-user first-person shooter. So don't blame my generation for first-person shooters, blame the generation before me for first-person shooters. Now the thing which is interesting about this is it was actually played on the ARPANET. Now the ARPANET is important because it was the precursor for the internet as we know it today. So even before we had the real internet, people were playing video games. Okay, so then after that, we had something called MUDs, or multi-user dungeons. This was developed in 1978, the year I was actually born, and this was developed by someone called Richard Bartle and Rob Tropshaw, and it was basically an online text-based chat room where you would log in and basically interact with the dungeon and with other people by pasting text commands. So if you ever played the ZX Spectrum game called The Hobbit, then you would be familiar to text-based entrances. Okay. Now, after that, the first what I would call real online virtual world was a game called Habitat that was developed in 1987 by a company called Lucasfilm. They've done other important things like Star Wars and Indiana Jones. And you can see that, well, at least compared to modern computer graphics, you know, there's something left to be desired over there. But for 1987, this was probably very, very amazing computer graphics. And what's interesting over here is they were actually interacting online with other peoples, with weird two-dimensional characters walking around. Okay. So, if we look for a definition of virtual worlds, there's no accepted definition, but I like this definition given by Richard Bartle, the guy that did the multi-user dungeons, and he basically said the following in 2015. He said, it operates using an underlying automated rule set, so it's got its own set of physics, which I think is appropriate. Each player has represents an individual in the world. Today we call that the avatar or the player's character. The interaction with the world takes place in real time. So if you do something, it happens pretty much when you do it. This is going to be important later on. The world is shared. You're not playing on your own or participating on your own. And then the world is persistent. So in other words, if you make a change to it and you leave it and you come back later, the change is still there. And other people might have changed it while you were away. And the last one, which I think is actually the least important, it's not the real world, just in case people were wondering about that. Okay. Now, there's been a couple of other ones. World of Warcraft, Ultima Online is a good example. There was a server ran out of the DSP lab a couple of years ago. No idea who ran it. So virtual worlds is something that we know. We typically call them MMOGs, or massive multiplayer online games. Okay, so that's virtual worlds. Let's go back to virtual reality. And once again, we're going to go back to where did this come from. So the first virtual reality device was the Sensorama, built in 1962 by someone called Morten Heilig. He called it the Experience Theater. Here is I think it's a photo, it might be a drawing of it, in 1962. And I think what's interesting over here is they had smell, wind, and vibrations, okay? We don't have that in our virtual reality at the moment. Here's a technical drawing from the patent, that's quite impressive for 1962. And the next virtual reality device that we see is in 1968, called the Sword of Damocles. It was basically a head-mounted display, although it was hanging from the ceiling, so head-mounted is maybe pushing it. And this was developed by Ivan Sutherland and his students at the University of Utah. Now, I think what's interesting over here is you can already see that this idea of stereoscopic vision is important for virtual reality, because that allows you to have depth perception, which means it increases the immersiveness. So if we go again and we say, okay, but what's the definition of virtual reality? Oh, sorry, I forgot. Before we get to the definition, in my opinion, nothing serious happened in virtual reality in the decades between. The next big thing in virtual reality was in 2011 when someone with the name of Palmer Luckey developed this prototype head-mounted display called the Oculus Rift. He did it in his parents' garage while he was 18, and he actually used the smartphone screen as the display. And eventually, I think Facebook bought it up and it became part of Meta and Facebook. And what's interesting about this device is that it had, once again, stereoscopic vision, but now they used special lenses and geometric predistortion so that when you put the device on, it actually covers your complete field of view, and it really does feel very, very immersive. I mean, it also causes simulation sickness in some people, but it does feel very real. So if we look at the definition of virtual reality, it's basically a computer-generated environment with scenes and objects that appear real, making the user feel immersed in their surroundings. Now, the following video, I think, very clearly illustrates this idea of feeling immersed in the surroundings.
Ja, en dan kijk je die andere kant toe, kijk dan naar papa. Daar is het. Oh, daar is het.
And that's what we want from virtual reality, that childlike wonder when we see the horse in the Minecraft virtual world. Okay, so the vision that we have for virtual reality, I think, is illustrated by this image from the movie Ready Player One, where you have the wizard, reaching out with his hand to the player, like Da Vinci, in that painting of Da Vinci. So this is the vision that we're striving towards. The current reality, though, given to us by Mark Zuckerberg, is slightly different at the moment. So I'm not the only one that's slightly disappointed in what Mark Zuckerberg is offering us at the moment. And I must also admit that, the question has been asked, especially with OpenAI and ChatGPT being released earlier this year. Is the metaverse dead? Has ChatGPT killed the metaverse already? After 3 years, we should go and bury it. Now, I'm biased, obviously, because I'm interested in this area, but I think to help answer this question, and we will get back to this question at the end of the lecture, I think it is helpful to look at some of the progress that has been made in related technology fields. And the technology field I'm going to talk about, or going to mention, is the advances in computer graphics or video graphics over the past 30 years. So here on the left-hand side, we have a game called Elite. It was developed by David Braben and Ian Bell in 1984, I think for the BBC actually, but it was available on the PC later on. I played it, it was awesome. Docking was impossible. And then only 30 years later, we have its successor called Elite Dangerous. And that's not comparable. The graphics are amazing. It's really amazing what they managed to do in just a period of 30 years. So I think to say that the metaverse is dead after only 3 years might be a bit premature, but I will return to this question at the end of the lecture. Okay, so This is a bit of history, metaverse, virtual reality, virtual worlds. So in the rest of the lecture, I'm going to move away from graphics and head-mounted displays, and I'm going to talk about infrastructure needed for building immersive worlds. So going back to that definition of Richard Bartle, we said there's the characteristics. It must have underlying rule set. It's physics. We're going to call that the world logic. Each player has its own avatar. Interactions take place in real time. Real time is important. The world is shared, and the world is persistent. Okay. So if we look at a virtual world, there's a bunch of elements here. The elements are things like, in Minecraft, which I use often in my research, it's blocks, you have textures, you have non-player entities like slimes, there's player entities, there's items, there's weather. And you basically, the virtual world infrastructure needs to keep track of everything, right, in real time. Now, one of these blocks in Minecraft is called a chunk. It has about 65,000 blocks in there. They can be stone, they can be wood. And for instance, when you connect to a server hosting a virtual world, it sends you about 400 of these chunks. So that's quite a lot of information that the server has to keep track of, and that has to be pushed to you. And this snapshot, like freeze frame of the virtual world, we call that the world state, and that's basically the exact values of the virtual world at any single moment in time. So what we do, or how this works, basically, is that you take this world state, you store it somewhere on a server. That server is connected to the internet or network, and then users access the virtual world using what we call a client application or a networked client application. They're also connected to the internet, and this runs on their home computer. And they basically, that's how they access the virtual world. There are some ways of using more than one server, which I will get to a bit later on. And then the rules for how the world works, how you move around, how you place blocks, what are legal actions, what are not legal actions, that's determined by the world logic. Okay. So to start, we basically have this idea of the server has the whole world. We call that the global state. The client initially has nothing. Then the client, when it connects to the world, it gets a portion of the global state. So it only gets a portion of this information. The reason why you send that to the client is because it's more efficient if that information is stored on the user's computer. It's much more quickly to go and access it and interact with it. And now if you do something, like you place a bunch of blocks, you create a little lake over there, that change only happens on the home computer to the local state. So if you want to share that with someone else, you first have to send it back to your server. The server then has to go and, check that the changes are according to the logic of the world. If it is, it accepts the change, and it sends a message to the client saying, yes, it's good. And then lastly, there might be other players in this area which are affected by this change. So the server has to go, and for each of the players in that area, it has to send a copy of the change. And we call these state updates. Okay. Now, the other advantage that we have here is that it is persistent. So if the client disconnects, now the changes are still here. If other players change it, when you connect again, you just basically get a copy of the local state again. Okay. So that's the basic operation. Okay. Now, how often does this happen? This change something, send it to the server checks it, send it to all connected clients. Every single time anyone does anything in the virtual world. Okay. If you have 1,000 clients doing one thing every second, there will be 1,000 times the number of clients affected. If you have 1,000,000 clients doing one thing every second, you have 1,000,000 times the number of clients' messages that has to be sent. That's a lot of messages that has to be sent, and this is one of the reasons why you can't use a single server to host a virtual world. You need many more servers because you have to distribute that load. Just like web servers work to an extent, but the problem is that it's now a world and you interact with other people. Okay, so how do we scale this? How do we make this work for hundreds, thousands, millions of users? Okay, so this slide is basically just a summary of what I just said. So we win a slide over there. So one of the things that the server does is you want to limit this communication. And typically, your clients are only interested in what happens around them, right? Because you can only see so far in the virtual world. So if something happens far away, you don't need to know about it. So we use what we call interest management or area of interest management. So the area of interest is basically the portion of the virtual world which is of interest to a specific user. So if you're in this area over here, you only send messages related to that area, and the server only sends you updates related to that. Something there changes, the server doesn't send you that. Only when you move to that area will the server start sending you information about that. So that's a way of limiting the communication. It doesn't solve the problem, it only makes it better, but this is kind of the best we've come up to now. Okay, so we're getting there. The next thing I want to talk about is basically scalability approaches. So we can't basically run this on a single server. We need multiple servers. So what are the approaches used to make more servers so we can handle more users? And there are three approaches. The one is what we call distributed server architectures. The second is what we call, tot ziens Annemarie, replicated server architectures. And the third one is what we call a hybrid server architectures. Okay. We're going to get to the videos just now. Hello, Johan. So it's like students coming into a lecture. You're used to it. Okay, so the first thing is what we call spatial partitioning or zoning. And the basic idea is you take your world, you split it up into different zones, non-overlapping, and each zone is hosted by a single server. Okay, so the one server doesn't have to do the whole world, it only has to do a portion of the whole world. And what's important over here is that the servers actually communicate to each other. So if a client was in this area and it moved to that area, well, that server is communicating to it, so the client would disconnect over here, it would connect over here, and then you could see that portion of the world. There is a bit of a question of what happens if you stand on the border peering across the border? Do you simply see the void, as in the 13th floor, also a common movie? You know, what do you do over here? There is an answer to that question. I will get to it now. But this is called spatial partitioning. Then we have, under replicated server architectures, something called sharding. Okay? Sharding is a word that actually comes from the game Ultima Online, because the world was shattered into shards or something like that. And the idea was that you have completely separate copies of the same virtual world. It's kind of like the multiverse if you watch Marvel movies. Okay? So if you log in, you have a choice of different servers in which you can log in. Each one is basically a copy of the same virtual world. At the moment it was created, but there are different players on it. They have done different things to the virtual world. So if you are in the one world versus the other world, there will be differences between them. And if you're logged into the one world, you can't actually interact with people in a different world. Okay, so it's basically a way of saying, how can we have more players play our game? Let's just have more servers with copies, and then we've got a European server, an American server, and an Asian server. Never an African server, but anyway. Okay. So this is called sharding. This is used quite a lot. I think Roblox actually use a version of this as well. And then lastly, we have what we call, then we have mirroring. Now mirroring is interesting, to me at least. So what you have is you still have multiple servers, and they have multiple copies of the same world, but once again, you allow the servers to communicate to each other. So let's say you have the red entity over here. On the blue and on the green server, there is a copy of that red entity. If that red entity moves, the red server will send messages to the other servers, and what they call shadow entities will move as well. So if you're logged into the blue server and the red guy moves, you will see that change, although you're logged into different users. So that's called mirroring, and that's a way of solving this problem of what happens on the border. Okay. And then lastly, we have what we call hybrid server architectures, and this is kind of a combination of all the previous approaches. It's the most complicated version. This was done in 2010, I think, for the US Army, the distributed scene graph. And the basic idea is you've got spatial partitioning, you've got mirroring, but you also take other functionality like scene rendering and message dissemination, and you basically say you servers are responsible for that, and you're responsible for that. So you share the work of actually hosting the virtual environment. Okay, but I'm going to talk the least about this type of one. Okay, so that's the theory part of the of this lecture. Now I'm going to talk a bit about the projects that I was involved in, which I think is the most exciting part. But anyway, so the first project that I was involved in was something called the Third Life Project. Okay. So the Third Life Project was an art and science collaboration which culminated in a 3-day performance in the Vuk Theater in Vienna in 2015. Okay. I play the trumpet up to matric, but I'm an engineer. As I told, my wife is a musician. I can play a musical instrument. There's a difference. Okay. I never would have imagined that I would perform in a theater in Vienna, but lo and behold, we were part of a presentation in the theater, and we only found out this about a couple of days before the performance, but anyway. So what happened is that we had these two crazy Austrian artists, Otto and Milan. They approached a colleague of mine from Norway to do this project called the Third Life. So the origin of Third Life is that you used to have this thing called Second Life. So this was an online game, and the idea was that just as you have your first life in the real world, you know, studying, eating, doing all kinds of normal things, you have your second life in the virtual world, and then you do, I guess, similar things. I didn't really understand it ever, but that's the second life. And then these artists were like, but what would happen if you allowed the virtual world to influence the real world again? And they called it the Third Life. I mean, it's art. It doesn't need to make sense, right? So we were part of this project, and there should be a slide up here. So Otto was the actor performing in the Minecraft world. He had an Oculus Rift because he was in VR. He had a Leap motion controller there, so you could use hand gestures to control the avatar. And he had this camera on top so that we can track where he was walking. So he had this red carpet, and as he was moving around on the red carpet, his avatar would move in the Minecraft world. And if he wanted to move long distances, he would stand in this border, and we would call it scrolling, and he would keep on moving, but he could change his direction by basically moving the direction his body was facing. Okay. Milan, on the other hand, was the actor in the real world. He looked like a Minecraft character somehow. And then there was these devices like trampolines and switches and stuff, Internet of Things devices. And then by Milan doing things in the real world, it would affect the virtual world. And by Otto doing things in the virtual world, that had effect on the theater, like the lights going up and down and things like that. But art, once again. So one interesting thing is they actually built a replica of the theater in the Minecraft virtual world. So as you sat down and you looked at the theater, you saw the setup, and then you saw it on a screen, the replica in the Minecraft world. And they also built a replica of the MoMA, which is the Modern Museum of Art in New York, I believe. So we were basically responsible for the virtual reality headset and the interaction, and the Germans were responsible for the Internet of Things devices, and my Norwegian colleague were responsible for the camera tracking device so we could know where Otto was standing in the virtual world. And this video basically is just a short demo of how it looked.
The question about virtual reality is not, is it true, but does it work?
Hello, I am here in a fantastic virtual world. I can also manipulate with my hands. Okay, Jason, I think you will help me to scroll in my inventory because there's so many TVs.
So this is the team that did it. We were the guys in green, the Stellenbosch team. We did not have an EU project. The green guys, the blue guys were the German team. He's actually a South African alumni, Corneille van Dalen. He did his master's with you, I believe. Did his PhD with Gregor. Orange was the Norwegians, although he's a German. This was the crazy Austrian artist, and this guy the server on which everything ran. So that was quite an interesting experience. Okay, so that's the VR part of the projects I've been involved in. So going back to 2013, when my students and I, John Gilmore was my first student as part of the MIH Media Lab, who got involved in gaming. John is unfortunately not here. He's working for Amazon nowadays, but his wife is actually a lecturer in our department. No nepotism there at all. So when we started working on virtual worlds, one of the things we discovered when we read the papers is that it was all these very theoretical proposals, and at most, they would test it in some kind of a simulated environment, okay? I mean, it's a lot of computer scientists which were involved in it. And us being engineers were like, okay, cool, but did you build it? Does it work in real life? So the gap we saw was that no one had developed a platform using a real online game in which you could test these ideas and check, do they actually work? What is their performance in real life? And thus, the Kukapan project was born. Okay. Now, it is a proof of concept multi-server network architecture for a single contiguous virtual environment. Contiguous basically just means there's one world and you can move around and the different parts of the world is just stored on different parts of the servers. And we used Minecraft for it because you could mod Minecraft. So we could get a game that we could adapt, but it was a real game used by 30 million people. The name Kukapan is actually an Afrikaans name for a mine cart, right, the Kukapan. And I was involved, I read about all these EU projects and I could never pronounce their names. So I thought, okay, I'm going to choose an Afrikaans name that they can't pronounce, and it worked. So it runs on 120 Raspberry Pis. So Raspberry Pis look like the following. This is a Raspberry Pi. It's about a credit card-sized single board computer. It's basically as powerful as a powerful desktop computer that I used when I studied. 120 of them. Thank you, Faculty of Engineering, for sponsoring that. Yes, it stands in my office somewhere. It uses about as much power as one of these oil heaters. And the idea was we want to demonstrate at least 10,000 users simultaneously participating in this world. We're not there yet, but that's the idea. So we start with our world. We split it into zones using spatial partitioning. Then each of the zones are actually, we've got a Raspberry Pi hosting that part of the zone. But now, because we actually want it to be, users must be able to migrate between the regions, so the servers must be able to communicate with each other, we basically have the servers form what we call a peer-to-peer networking overlay. So the advantage of that is that it self-organizes, so you can add Raspberry Pis or remove them, and they figure out amongst themselves how to communicate with each other and how to send messages. And then what we do is so now we've taken care of hosting the world, now clients need to connect to it. So instead of the clients connecting directly to the server, we actually use what we call a proxy server. So the client connects to another machine, and that machine actually is the one that if you move from one zone to another zone, it would disconnect from this zone and connect to that zone again. And the reason for using a proxy is because you want the user not to be aware of the fact that he's being migrated. So if his connection is not interrupted, then it will appear to him as if, everything it's just one server you're on. And then the last bit of magic we need is this mirroring. So anything which happens in the one zone is duplicated on all its neighboring zones. Okay, so that's basically the vision that we had. We built that. So we first did a proof of concept at the end of 2013, I believe, which is this video over here. And what you will see is on the left-hand side, you will see a user connecting directly to a server, and this one was connecting through a proxy. So we wanted to check, does the proxy break it? And the good news is there's no sound, by the way. So the good news is it seems to work. The proxy doesn't add any additional latency. You can see that's Urban Sammy, my brother's username, and you can basically see places, blocks, everything works fine. But this is just with a single server, so then what we do is we add another server by hand. They form a distributed server cluster, And then what can happen is that now urban Sammy can actually move, and this is where the boundary between the two regions was. So urban Sammy will now go and cross it. There's some migration artifacts, but he's actually connected to a different server, but this user, it just looks normal for him. He will place blocks. Any moment now, he will place blocks. There we go. And you can break things and do things like that. So this was the first prototype system to check will it actually work. There are issues. You will see now that when he migrates between regions, there are these migration artifacts. There you can see it. Takes a while, but then he's logged into the other side. But in principle, it works, and it works in real time. That's the important part. So 3 years go by, we get a bunch of Raspberry Pis, and then we basically build a bigger system. And what you see over here is our test of our spatial partitioning system. So what you see over here is what we call a Voronoi diagram. And each of these little houses over here basically represent a single Raspberry Pi being added to the server cluster. This is a sped up video. This takes about 30 minutes to go from one server to about 120 servers. But you can see, as you add each new server, they basically figure out amongst themselves, hey, who's my neighbor and which part of the virtual world am I supposed to have? And you can add them, you can remove them, it works, mostly. Okay, so now we have the spatial partitioning working. We can have 100 Raspberry Pis in it. It makes your office nice and warm in winter. And then the next video is where we basically show client migration. So I'm just going to have to pause here quickly. Yes, so I need to explain something. So what you see at the top over here is kind of the global view of the spatial partition. And what you see here at the bottom is kind of a local view of the spatial partition. So this red region over here is actually that region over there. See, this should have been at the top, but anyway. So that red region is that region over there. This region over here is that region over there. So you can basically see that's a copy of that. And what happens is the client will now log into, I think, this region over here, and then eventually, and then it will be moving backwards, and then it will be migrated. It's going to appear here any moment. There we go. And you see there's none of those visual artifacts anymore. I mean, there's this little message over here, but that's fine. And you can see it will move back up again. It will migrate again to the top region over there. So we could actually have a Minecraft client. This is a real Minecraft client. We haven't modified it. And we have the Minecraft hosted on 120 Raspberry Pis, and it works. Okay. You'll see that theme, it works. I like that theme. Okay. Then the last thing is that, okay, we want to test this with 10,000 users, right? Now, it's kind of difficult, even at a university, to get even 100 students say, hey, can you come quickly play Minecraft for 10 minutes? I want to test if my system is working, right? Oh, there's a line of code missing. Okay, just wait a minute. Okay, then we run the experiment again. So, I mean, it's difficult to get people to test your system. So our solution to that problem was to basically write what we call a client emulation. So we basically wrote software which basically, from the server's point of view, is just a normal Minecraft client. And what you see over here is a bunch of them. They're running in a square over here. We have switched off mirroring at that stage because it uses a lot of communication. But you see them running, and at some point they will disappear because they're being migrated to a different server. And then they will appear again because they're migrated back, and they keep on running. So we can use this to test our system now. Okay, so that's great. 120 Raspberry Pis, have a bunch of clients. We actually did a test. I think we got about 600 or 800 clients over the 120 Raspberry Pis, and we were fairly happy with that result. And that was good. And then I became head of the department, so my research slowed down a bit. But anyway, we're still working on it. But there's a problem with this server-client architecture, and some of you might have spotted this already. The problem with the client-server architecture is that for every single change in the world, every time you place a Minecraft block, the server has to send a message to all affected clients. And as I said, if there's 100, you need to send 100 messages. If there's 1,000, you need to send 1,000 messages. If there's 1,000,000, you need, for that one single block, you have to send 1,000,000 messages. And for some reason, that should not have happened. Where are we? Let's go back. There we go. Okay. So the problem here is the number of update messages a server has to send scales with the number of affected clients. For computer science terms, that's the order n scaling of your algorithm. That's bad. You don't want order n algorithms. Okay. You want log n or order 1. That's even better, right? And yes, you can use multiple servers, but you're just going to run into the same problem again. Now it's just a higher number at which there's too many clients on a single server. You have to send too many messages. It's just not going to work. So we need to fundamentally change the way we send the messages, right? Now, the thing is the server sends a duplicate message. So can't we change the system? Instead of sending n messages, for where n is the number of clients, we send one message, and something else takes care of making certain that all the clients actually get the number of messages. Now, there is something that does that. We called it the publish-subscribe messaging paradigm. Okay. And you're like, what? Now, you already know what this is. If you've used Twitter or Facebook, or X or Meta, whatever their new names is, you already know and have used publish-subscribe. So let me explain to you. So Twitter, I'm going to use Twitter because I can't, the other name is wrong. So Twitter has their Twitter servers. We call that the message broker. So when you publish a message, when you tweet, you're sending a message to Twitter on your own channel. Celeste has a Twitter account. Celeste, civil engineer, I don't know. So when she says, we passed our EXA accreditation on Twitter, she sends a message to the Twitter server, and then everyone who has followed Celeste in civil engineer, they have subscribed to her channel, and then the Twitter server says, oh, you have 1 million followers, I'm going to make 1 million copies of the message and make certain that they all get a copy of the message. But the server publishing the message sends one message, and then some other thing takes care of making the copies and sending it along. Okay, so, yay, publish, subscribe. That will solve our problem. Well, it will move our problem to some dedicated machine, which is just used for communication. That's the basic idea. Now, yes, but the problem, this works for Twitter and for Facebook and all these type of things, but the problem with virtual worlds are that when you do things, inherently you're interested in what's going on around you, right? I want to place a block there, right? Someone else is standing over there. He needs a consistent view. So something which is close to him, that's how you determine whether he gets the message. If the update happens within the area of interest, that's how you determine whether you send the message to the client. So inherently, we need publish, subscribe, but it's not channel-based, but it needs to be location-based or spatial-based. Now, once again, fortunately, I have a colleague called Xunyun Yu, and Xunyun Yu came up with this concept called spatial publish, subscribe in 2009 or 2010, and we have been collaborating since, he examined John Gilmore, for instance, and we've been collaborating since 2019 on this project called VAST, which is basically spatial pub sub integrated into our Kukapan project. And I mean, the basic idea is that you publish messages to a specific area, you subscribe to receive messages in a specific area, and if your publication area and your subscription area overlaps, you get a copy of the message. If it doesn't overlap with the subscription area, you do not get a copy of the message. Okay. So it's pub sub, just with a spatial aspect. Okay. Yes, this is exactly what we need. So we developed the library. I had a mechatronic Scripsy student, actually, who did a lot of the software for that, developed the library further, and then we basically applied that to our Minecraft context. And instead of having a single proxy between our client and our server, now we have a client proxy and a server proxy, and we have our spatial pub sub matcher here in between. Okay. But the bottom line is that your server can now, so you have your server over here, it subscribes to receive everything in the area under its control. if a client goes and it moves, it publishes its event. If it falls within the server's area, it will receive the message. And in the same way, the server, we remove the interest management, and it only has to send a single, oh yes, let's start writing. See, this is what happens if you talk too long in your presentation. Oh, this is going to be fun. We're back. Yay, we're back. Yay. Thank you. The MMOG. So, where was I? This slide. Okay, so basically our server only needs to send a single message now, and our broker, our spatial cluster broker, will take care of making certain everything gets the message. So this is the idea. Does it actually work? And the answer is, well, it does. So my master student sent me this video quite recently. So this red area is the server's subscription areas. As the client moves, you can see the red part moving as the client moves. And those red blotches are basically when it does something in the environment. And the good thing over here is it works in real time. So using spatial PubSub is a valid alternative to the normal server client architecture. And in this part over here, we now just wanted to know, okay, but if we spawn a bunch of pigs, we love pigs in Minecraft, and we let them run away, so once again, does it work? Yes, we get the messages, so it does actually work. Okay. So that's the good news. We took Minecraft, ripped out the server client architecture, we put in the spatial PubSub architecture, and we demonstrated on a real MMOG that it does actually work. Now we are doing science over here, so we do actually measure things as well. So what we did is we basically did an experiment with one server from 1 to 6 clients, and then we said this is the normal Minecraft server which you download from Microsoft, and as you can see, one client 30,000 messages in 2 minutes, 6 clients, that's about 300,000 messages in 6 minutes. That's a lot, right? This dark green bar over here, that's what we call a optimized Minecraft server. So people took Minecraft, made it slightly better, made it open source. That's what we base our modding of the Minecraft server on. But it's still server client, and you can see, yes, now you only have 7,000 messages for one client, but it still increases quite. You have that's about 100,000 messages per day. And then this bottom line over here, that's Spigot, but with spatial PubSub. And you can see over there, we have a 6 times reduction in the number of messages sent from 6 when we have 6 clients. And you can see that the increase in the number of messages is low, which is what we want. So then we were worried about, okay, but what about the memory uses of the matcher? Didn't we just move the problem somewhere else? So we measured the amount of memory that the matcher uses. This is 1 client, 2, 3, 4, 5. And yes, there's a big jump from 1 to 2, but the amount of additional memory you need increases as the number of clients increases. So this would seem to indicate that it's going to level out at some point, and this is also really a scalable solution. And then lastly, what we did is we measured the added delay as a result of putting this thing in the middle, the matcher, and we measured how much delay are we adding to the messages being sent. And we see on average over here, it's about less than 50 milliseconds. That's 100 milliseconds, it's less than 50 milliseconds. You might be wondering what's going on over here. That looks more than 100 milliseconds. So this is each time a client connects to the world. And you remember those 400 chunks of 60,000 blocks? That's basically all that data being sent. That takes some time to send it. So we're ignoring those for the moment. And we're normally focusing on, okay, but what's the normal operation? And we see, and the magic number is less than 100 milliseconds is good. That's what you want when you, that people don't see delays of less than 100 milliseconds. So that's it. Okay, so I've shown you 3 projects in which I've been involved in. This slide I got yesterday, so this is really hot off the presses. I just want to add these are some of the publications that came out of this work. You can see there's the timeline project over there, some more. We do actually get some publication out of this as well. It's not just games. These are some of the postgraduate students that has been directly involved in my work on the scalable virtual worlds. This is the guy that did this experiment you just saw. That's John Gilmore. And then these are just some of my collaborators and funders. At the top, Gregor, Karsten, Gregor, and some of the other people which I collaborated with as well. Now, I'm nearly done. I want to get back to, nearly done. So let's talk about the remaining, or the conclusion, or the remaining challenges. Except your mouth getting dry. One of the other remaining challenges is we can see that there has been significant strides in building the metaverse, right? I mean, our computer graphics is amazing. I mean, what you see, you nearly can't distinguish between is this computer generated or is this actually a camera thing. So it's amazing with the computer graphics. And the virtual reality technology has also come in leaps and bounds. You can now go and buy a virtual reality headset with controllers. My good friend Isak has a pair that you can scare yourself in some horror 3D environment. Works very well, so commercially they're available. What we haven't done yet, we haven't really built architecture that can scale to millions of users. Yes, for websites, not for virtual worlds. Okay. So we need to figure out how to do that. And I think part of the answer is we need to distribute work better than we've been doing last time. The second thing is we need to increase our immersion. We need better virtual reality tools, right? Now that's not my field of interest, so it could be full body suits, it could be brain interfaces like Elon Musk is working, I don't know. But if we get better immersion technology, that will obviously also help in building the metaverse. And then the last thing I think which is necessary is we need very low latency communication. Now the reason why this is important is that if we add augmented reality, which is the virtual elements in the real world. So imagine you were all wearing virtual reality goggles, and as I was holding up my hand, there was the earth spinning over here or whatever. And if I, turn my hand, it would spin faster or spin slow. This needs to happen quickly enough so that everyone has a consistent view. If I turn my hand, but for Thomas Nisler, there's like half a second delay before it starts spinning, that's going to break his immersion. It's like watching the Rugby World Cup final on SABC streaming while your neighbor is doing it on Beast TV. And they cheer because their packets came first before yours. It breaks the immersion, right? So we need better communication. Okay, that was it. Now, if you asked me 2 months ago, has there been any major developments in this space? My short answer would have been, not really. However, about 3 weeks ago, a company called Cloud Imperium Games, they're developing a game called Star Citizen. They have been developing it since 2011, I believe. One of the reasons why they are famous or maybe infamous is they had the largest Kickstarter fund ever. I think they've spent something like $600 million on this development over the last 10 years. So we could maybe solve load shedding with that, I don't know. But they announced about 3 weeks ago that their one version of the game called Squadron 42 is feature complete and people can actually start playing in the next year or so. So I was like, wow, is this real? And I went and read some of their, they've got some videos about their technology and how it works. And they've got things called server meshing, they've got things called persistent entity streaming, they've got something called replication layers. And when I read those, I'm like, this sounds very similar to some of the things we've been working on in the past years, which is trying to solve that scalability problem. So I think you need to watch these guys. I think they're actually at the forefront. And as an added bonus, you've got Luke Skywalker there, so it must be good, right? That's Mark Hamill, by the way. They Luke Skywalker. It must be. Okay, now I will end, and I want to get back to this original question I had about did OpenAI, did ChatGPT kill the metaverse? And I'm obviously going to say no, right? But let me appeal to authority. Let me quote what someone else said.
This someone else is actually his name is Vishal Shaw. He is Meta, or Facebook's vice president of the metaverse. So he's basically in charge of Facebook building the metaverse. And he had the following to say. He said, and I quote, "The hype in the metaverse is dead. And this means now we can put down our heads and we can start to build." Thank you. I've just seen this from the other side.
Good evening, Professor Herman Engelbrecht, to the Engelbrecht family and friends, Professor Vickers van Niekerk, Dean of the Faculty of Engineering, to our University Leadership President, Leadership of the Faculty of Engineering, colleagues, ladies and gentlemen. It's an absolute privilege and pleasure to be with you tonight, to be part of and shared in this inaugural lecture, which is effectively the introduction of Professor Engelbrecht and his academic scholarship and interest to the academic community at Stellenbosch University and our community at large. Now, the inaugural lecture is typically a rite of passage event within an institution, which marks the recognition of a colleague that has been promoted or appointed and enters the rank of full professor. In the case of Professor Engelbrecht, it is the recognition of him being bestowed the rank of full professor on being promoted within the University of Stellenbosch. This event affords the opportunity to Professor Engelbrecht to share with us his innovative ideas, his discoveries, and deep insights with regards to his discipline focus and his academic scholarship and interests. I have to say, when you start off your lecture talking about the Sinclair ZX Spectrum 48K, it brought back some memories. Because I remember my father bringing home one of those to share with me. And that was where I got interested in The Hobbit. So I could easily kind of reminisce about your experiences as well and getting into this field. And I also played the Habitat as well. Yeah. So those are the early days of the virtual world. And I have to say, you know, as if I'm thinking back to my teenage days, I think for any teenage gamer, you've got the dream job, right? Dream job. Professor of video games.
I'm going to claim that.
So thank you very much, Herman, for your lecture on building the metaverse. I have to say that it is probably one of the most intriguing and inspiring topics that I've had the privilege of listening to in terms of all the inaugural lectures that I've had to attend. It's truly inspiring to hear about the potential virtual worlds hold for transforming how we interact, how we create, and how we collaborate in the digital realm. And now your discussion about the technological challenges highlights the depth of innovation required to build a seamless and interconnected virtual world. And overcoming these hurdles will undoubtedly pave the way for a more immersive, a more inclusive digital future. And that's digital worlds and digital realities. The idea is that users can seamlessly transition between different virtual worlds and platforms opens up a world of possibilities, not just for gaming, but also for creativity, for commerce, and for social interaction. So thank you once again for this thought-provoking lecture. I'm excited to see how the metaverse concepts evolves and contributes to shaping our digital futures. Now, one of the indicators of a good inaugural lecture is the ability of the professor to share deep and complex disciplinary knowledge in a manner that is both understandable and thought-provoking to the general audience, but also clearly articulates the novelty and the complexity of the work of disciplinary experts. Now, this is an incredible balancing act, and you have done impeccably well this evening in achieving that, so well done. Well done on that. I've got a really good appreciation of not just the concept of the metaverse, but also about your work on the development of the underlying architecture and infrastructure. Your lecture tonight gave us a good understanding on how the infrastructure that is used to build the metaverse can be improved from a scalability perspective to develop indistinguishable worlds between real and virtual. Congratulations once again, Professor Engelbrecht, on your body of research and the work on the architecture of virtual reality and virtual worlds. I am sure that your research will significantly add to not just the academic scholarship in this field, but more importantly to us one day seamlessly moving between real and virtual worlds, enhancing our lived experiences. It gives me great privilege to present you with the scroll in recognition of the inaugural lecture.
Hi everyone, I'm Engelbrecht. I'm Herman's older brother, and it's a great privilege for me to say a few thank yous on his behalf. As his brother, not as the future SOP. Okay, I'd like to thank the following people: corporate communication, specifically Olivia Adams and Amira Brown for their arrangements, Justin Albert for the recording and the live streaming of the lecture, coordinated publications, specifically Jonathan Blankenberg within the Center for Governance and Function Support, the rectorate member, Deputy Vice Chancellor Learning and Teaching, Professor Duresh Ranjiganath. Thank you very much. I'm glad to see that I also have a kindred spirit there in terms of playing the Hobbit as a child. The Dean's PA, Martin Luperose, for the support in preparing for the lecture. And then the Dean's office staff, specifically Ulrich and Clint, for the preparations to get the rates all ready for this evening. Then, okay, these are written as my, but it's Herman saying these words. my wife, Marianne. I should say Herman's children. Maria and Adrian. Adrian for putting up with their grumpy father. My father, well, that happens to be my father as well. Delphi and our late mother, Suzanne, who taught him wat die zwaarste is, vir die zwaarste weet. My older brother, that is now me, Javi, for always being willing to listen, willing to help and being the voice of reason. Our twin brother, well, his twin brother, Skalk, the ethical philosopher. Herman's parents-in-law, there for raising such a wonder woman and life partner. Herman's mentor, Pietri Meyer, for seeing and nurturing his potential and for all the morning coffees. Herman's promoter, Juan de Prier, who shaped his early career. Herman's colleague and friend, Gert-Jan van Rooyen, for teaching him about not being afraid to try new things. Herman's friends and colleagues at the ENE department, I see many of them are here spread throughout the audience. And then also specifically, I think people who support him in his role as HOD, Johan Boysen, I saw Johan sitting here somewhere, Johanna Clear and Larry Borkel, Herman's collaborators, Gregor Schiller, Carsten Grewoods, and Chun Yun Hu, who accepted him as an equal. His first PhD student, John Gilmore, whom he started this journey, Prof. van Niekerk, for teaching him about leading a group of people. Sometimes we forget how large a group the E&E department is. It's quite a big department. His fellow chairs, I saw Johan van der Spy there, and colleagues in the management committee, Celeste as well, also Marley and Enzo, Herman's friends in the board gaming group. There are quite a number of them here this evening for all the fun times. And finally, I would like to thank Sony for their noise cancelling headphones during COVID. Pretty sure we're a bit younger. Then I'm ad-libbing this last bit. I just kind of want to thank Herman, I think, for taking on the role of HOD. He was still an associate professor when he undertook that. He stepped up to the plate. He, I think, has done a wonderful job of leading our department selflessly. I don't think it's a large amount of personal gain in that. And he's taken our department through some definite challenges. I mean, he was hardly the HOD, and then COVID came around. And I think he's probably one of the few HODs who has had two ex-officers, an interim visit and a regular, through no fault of his own, an interim visit and a regular visit. And he, with Vicky's support, pioneered the data engineering course. So, and if that wasn't enough, the whole E&E departmental building is being refurbished at this moment, and there's a lot of non-academic work that has to happen there. So, thank you, Herman, and yeah, thank you. I also have a better idea of what you're doing. Everyone who was here to support Herman, who made it to come here, and everybody who is online. Thank you very much.
Please stand and take the debate position for the
Thank you.